Welcome to the Explainer. Look, if you've ever stared at a screen showing full Wi-Fi bars but absolutely zero internet connectivity, you know the unique, pulling-your-hair-out frustration of a shattered network stack. Today, we're taking a definitive, professional-grade look at diagnosing and fixing a completely broken Linux network stack. We are going way beyond the basic just turn it off and on again advice. Instead, we're going to deconstruct the operating system's networking layers and rebuild them, literally, from the command line up.
Okay, let's dive into this. Here is our diagnostic roadmap for today's incident response. We'll start with the blackout trigger, move into the Layer 3 routing coma, fight the persistence battle, fix the DNS coma, and wrap it all up with system validation.
All right, part 1, the blackout trigger.
Every catastrophic failure has an inciting incident, right? To fix a system, you first got to understand exactly how it broke. Let's look at the exact moment your machine was cut off from the outside world. You might have run an experimental optimization script, maybe setting up a Cloudflare warp tunnel, or applying TCP/BBR congestion control modifications to transpeed up your connection. Now, these scripts modify deep kernel parameters, and they often flood your local router with non-standard packet requests. So your router's firewall panics. It sees this anomalous traffic and instantly throws up a protective lockout for every device on the network. The result? It's what we call a ghost connection. Your hardware is actively negotiating a signal, but the logical flow is entirely severed at the source.
If you're new to network diagnostics, just picture it like a hotel room. You've successfully walked into the lobby. The door is open, which represents your physical Wi-Fi connection. But you don't have a room key, meaning you have no authorized path to travel anywhere else in the building. And honestly, even worse, you don't have a phone book, meaning you can't look up where anything actually is. You are technically inside, but you are completely isolated.
Moving on to part 2, Layer 3 routing coma.
Let's drop down to the foundational routing level to diagnose our first major point of failure. This is where we separate the physical connection from the logical paths. It is absolutely vital to understand that Layer 1 and Layer 3 are entirely different beasts. Having 4 solid Wi-Fi bars in your system tray, well, that just means Layer 1, the physical radio wave connection, is healthy. It means literally nothing for your actual internet access if Layer 3 is broken, because Layer 3 requires an assigned IP address and, crucially, a default gateway to tell your traffic where to go.
And this brilliantly illustrates the core issue. At the heart of the routing coma are 0 default gateways. When you run your diagnostic commands and see this on your screen, your machine is trapped. A missing default route means your computer is like a sports car sitting in a driveway with absolutely no roads leading out to the rest of the world. Sure, it can talk to the printer in the same room, but it is totally blind to the internet.
So, how do we pave a new road? We've got to use the IP tool. But keep in mind, Linux requires strict discipline here. The syntax rule you absolutely must memorize is tool, then object, then action. If you panic and just type IP route default add, Linux is going to throw a fatal parser error. It expects the tool, which is IP, the object you're manipulating, which is route, and the action, which is add. Breaking this hierarchy means the kernel simply ignores you.
Picture the terminal cursor blinking as we type the exact kinetic command to fix this. Sudo IP route add default via 192.168.8.1. We are invoking super user privileges, calling the IP tool, targeting the routing table, and injecting a brand new default exit path pointing straight to our router's IP address. Hitting enter on this command forces that exit door to the internet backbone wide open. The packets finally know exactly where to go.
Which brings us to part 3, the persistence battle.
But hey, don't celebrate just yet. Opening the door via the terminal is only half the war. Now we face the volatility of temporary fixes, because we have to keep this network alive. The command we just ran, it lives purely in volatile RAM. Modern Linux distributions often deprecate or entirely remove legacy utilities like dhcPlient that used to robustly handle IP renewals in the background. Because of this, when your router forces a mandatory DHCP lease renewal a few hours from now, your system will wipe the RAM tables completely clean. The default gateway vanishes, and boom, your internet connection crashes all over again. We have to transition from temporary terminal commands to hard-coded, persistent settings. To make it permanent, we execute what I like to call the Ubuntu GUI dance. First, you dive into the network manager settings. You might find toggles stuck in weird states because of the crash. You need to switch off the automatic DHCP for both DNS and routes. Then you flip the IPv4 method entirely over to manual. Finally, and this is the absolute secret sauce here, you manually add a custom route with the destination of quad 0. That's 0.0.0.0, which tells the system to route absolutely all external traffic through your specific gateway.
So the crucial point is hard-coding these parameters. You assign a static IP, like 192.168.8.147, a subnet mask of 255.255.255.0, and set the gateway to 192.168.8.1. Just a quick warning here for the professionals. Whenever you hard-code a static IP on a local network, you risk an IP conflict if the router's DHCP assigns that exact same address to another device, like a smart TV, later on. So always pick an IP high up in the subnet range to minimize that risk.
Let's shift gears to part 4, fixing the DNS coma.
Okay, so we have routing, and it's persistent. But if you open a browser right now, it will still fail. We've hit the final major hurdle, the translation layer failure. Let me ask you this. If you pull up a terminal right now and type ping 8.8.8.8, you will see successful packet returns. But if you type ping google.com, it instantly fails. Why? Because while the pipes are firmly connected, the system has absolutely no idea how to translate human words into machine addresses.
We have the map, which is our routing, but we have lost the phone book, which is our DNS. When your browser tries to look up a website and fails to find the IP, it throws that infamous Chrome error code DNS probe finished bad config. Basically, we need to repair the operating system's internal phone book. To fix this, we actually need a really quick computer science lesson on the file system. In Linux, the file /etc/resolve.conf isn't supposed to be a real static file. It's supposed to be a symbolic link, a dynamic pointer directing the system to an internal stub resolver that manages DNS actively. Those optimization scripts we talked about earlier, well, they often delete that dynamic pointer and replace it with a frozen, dead, static file pointing to a broken inode. So the system looks for live DNS instructions and just hits a brick wall.
Here is the exact recovery suite to fix that file system logic. First, we forcefully delete the static gunk. We run sudo rm-f/etc/resolve.conf. Now that bad file is gone. Next, we rebuild the dynamic link using the ln-s command. We type sudo ln-s/run/systemd/resolve/stub-resolve.conf/etc/resolve.conf. This acts literally like reconnecting a severed nerve in the operating system. We are pointing the network manager back to the correct live DNS translation service.
Now, in some extreme cases, your internet service provider might be running restrictive, transparent proxies that block standard DNS resolution even after you fix the symlink. If you find yourself in this situation, you need a highly technical command line fallback. You can actually bypass the local stub resolver entirely by using an echo pipeline. By typing echo nameserver 8.8.8.8 sudo t/etc/resolve.com, you forcefully pipe Google's public DNS servers directly into the configuration file, bypassing the ISP's local restrictions and guaranteeing external translation. A real game changer if you're stuck. Finally, Part 5, System Validation. So we've cleared the routing coma, we've enforced persistence, and we've repaired the DNS translation layer. Now, we enter the final phase. Professionals never assume a fix worked. We prove it. We use a two-tiered validation checklist. First, you run ping 8.8.8.8. If the packets return, you have mathematically proven that Layer 3 routing is functional. The gateway is open. Second, you run ping google.com. If this works, you have proven that the DNS translation layer is successfully mapping domain names to IP addresses. Seeing both of those ping commands return successful packets is the ultimate validation. Your internet stack is completely rebuilt. And this brings us to a really crucial takeaway. Graphical user interfaces are super convenient, for sure, but when the system truly breaks down, deep knowledge of the underlying OS architecture is your ultimate safety net. Understanding the exact command line plumbing of Linux networking doesn't just let you fix your computer, it empowers you to control it absolutely. So I want to leave you with this thought. If a single experimental script can instantly sever your digital lifeline, what other fragile ghosts are hiding in your operating system's kernel right now? Keep learning, keep exploring, and I'll catch you in the next one.